Dear attendees, I would like to present you our research on a topic: development of an algorithm for identification of damage types on the surface of sheet metal. One of the important elements of modern metallurgical production is quality control of wrought metal. Electron microscopes are widely used in nanotechnology and material science for examining surfaces at high resolution. The morphology of scratches on surfaces plays a crucial role in determining mechanical properties and wear resistance. Therefore, accurate identification and characterization of scratch types are essential for improving product durability and reliability. Detection of metal surface defects traditionally is implemented taking into account machine vision. However, complex scratch shapes and wiring orientation pose challenges due to data collection conditions variations. Instead of solely relying on contour-based visual cues, our strategy focuses on utilizing signal analysis techniques to extract relevant temporal characteristics and spectral frequencies associated with scratch morphologies. This shift empowers us to concentrate on the extracted contours themselves and enables exploration of fresh face sets related to scratch morphology. Since scratches may exhibit various orientation, our proposed method employs time-invariant properties to maintain consistency throughout all angles. Specifically, we utilize power spectrum density calculations to assess frequency components independently of phase considerations. While deep learning models require vast amount of laboratory training data, our method requires less laboratory training data, making it significantly easier to integrate into existing microscopy systems with minimal modifications. Our approach potentially uncovered new informative features and workflow diagram present on slide number 7. Our approach consists of a few steps. Step 1. Image preprocessing. We convert RGB images to the grayscale. After that, we apply Gaussian filtering and normalize pixel values. Step 2. Binarization. We utilize Otsus thresholding techniques to create binary images. Steps 3, 4, and 5 are morphology image processing. We utilize morphology function to remove unwanted pixels from binary images, and we apply morphological closing operations to fill narrow gaps. Steps 6 and 7 are identification of borders and centroids. That's essential part of our research, and we identify the borders and centers of mass of each object in the context of surface scratch analysis. Step 8 is feature extraction. We extract time-invariant features such as power spectral density from centroids and border information. Figure number 1 show an example of proposed metal surface damage that are input images for the row number 1. Row number 2 is example of identified pseudocolored metal surfaces and appropriative object identified and pseudocolored. Row number 2 and row number 3, example of converting contours of metal surface damage types. For appropriative classes attrition, line, and scratch. Figure number 2 demonstrates a power spectral density feature extracted from metal surface damages types for appropriative classes attrition, line, and scratches. And slide number 15 demonstrates a three-dimensional principal component analysis representation. The distances, appropriately minimum, median, and maximum, mentioned here, between centroid coordinates of clusters in the first three principal component analysis, mentioned here. These measures provide further insight into the distribution of the dataset of the reduced dimensional space obtained via PCA transformation. Slide number 16 demonstrates conclusions. Thank you for your attention.